When you see the word in a sentence that says something is always true or always not true, be careful. Because there are very, very few things that are always true or always not true. The question I gave you on the quiz was middle is always more accurate. And there's a couple possibilities when that is not true. Claire came up with that example because left, middle, and right are going to be exactly the same if you've got a constant function. Boom. Almost always, except there's one example of when it isn't. The other example of when it isn't is if you take the limit as n goes to infinity, they converge. And somebody, and I don't remember who, came up with that idea as well. It's like, yeah, so middle, or excuse me, left is going to be a little bit less, middle is going to be a little bit closer, and right is going to be a little bit above. But the limit of these three as they go to infinity converges, and you can very quickly get it to converge to thousands of decimals, which means that the accuracy becomes irrelevant at that point. When you take the limit as something goes to infinity, you're basically saying these just get closer and closer and closer until the point where they're, to all intents and purposes, the same accuracy. You know, if something's accurate to 500 decimal places, you never care anymore. Nobody cares. You're never going to need something that's accurate to 500 decimal places. So this, I think, is the best example of not always, because look, they're equal. But another decent explanation is these get closer and closer and closer to the point where it really makes no difference if you just keep going far enough, all right? So watch out for that word. Watch out for that word. Trying to think why it would matter outside of academia. Tests like to do that. And I think the reason they like to do that on testing, you know, calculus, more advanced classes, the reason they like to put that into test questions is that they want you thinking about exceptions. And so where this comes into play in real life is probably before you apply a solution, you really need to sit down and figure out if there are any reasons why that solution is not appropriate. Oh, here's a situation where we're going to do this. Whoa, hang on a second. There's this reason why that's not appropriate. You know, a really simple one would be welding. You're welding up pipes for water to flow through. There are kinds of welding that you just flat out do not want to use if there's going to be salt water running through your pipes, because the salt water will eat away at the welding materials. And so this is the normal way to weld pipes. Uh-oh, we might have seawater in our pipe. Don't use that kind of welding. So just be thinking about that. Be careful with it. And anytime you start seeing the word always in something, start thinking, oh, is that really true? Or is it mostly true? Is it mostly always? All right. Questions? Okay. And now that I've mentioned it, it's bothering me even more. Might have to take off my shoes and wander around in my socks all day. Or tighten my shoelaces. All right, guys. Last thing we talked about yesterday was average value of a function. Let's just recap average value. We've got some function. We want to know the average value between these 2 points, A and B. and somewhere in here in the middle is this average value. And the way we do this is we say, well, let's take the area of the function and let's divide it by the width of the function. So anytime you see, the words average value of a function, all you got to do is find that area right there, divide it by the base, and basically what you're doing is you're saying, well, then we can approximate it as a rectangle. If I look at this function, if this is the average value, that area is the same as that area. So you're just working backwards from take the area, pretend it's a rectangle, divide it by the width, boom, you've got the height. So that's the gist of what that means. So what we had discovered yesterday is that if we say that the average of f occurs at f of c, we noticed in the two examples that we did that c had to be in that interval. Both the examples that we did, the average value of the function, hey, you know what, I'm going to do this because it's like less ugly, occurred somewhere in that interval on both of them. Not coincidence. The average value of a function has to occur in the interval that you're calculating. This is called the mean value theorem of definite intervals. So the mean value theorem, actually, you know what? Let's put that. The mean value theorem, and yes, it's called the same thing for a reason, because it is the same thing. Remember, the mean value theorem had to do with slopes. The mean value theorem was if you're going from A to B and you draw a secant line, the slope of that secant line, there must be some point inside the function where the slope of that is equal to the slope of the secant line. Well, it's the same thing. The mean value theorem says that if you're going between some interval and you've got this thing happening in between, or you got this thing happening, it must happen in between. Average must occur in the interval. So the official language, one, if f is continuous, on the interval AB, again, function suddenly just jumps, it doesn't apply, then at some point C in AB, f of c equals 1 over b minus a, and this is the average value function. What use is this? The use of the mean value theorems in general and the intermediate value theorem that we talked about earlier, the use is that you can start with the assumption that your number exists. And so you're not spinning your wheels trying to figure out something that doesn't actually exist. And that's really, really nice when you're working on a project. You know, hey, we're gonna do a project to accomplish such and such a goal. Well, can we accomplish such and such a goal? Oh, absolutely, positively. Now, if this doesn't, if you couldn't prove it was true, well, then maybe you're going to explore it anyway. But you're exploring something with no idea whether or not there's an actual answer. Whereas in this case, you can say, yes, there's an answer. It's a lot easier to find something when you know there's an answer than if you're sort of speculating that maybe there's an answer. So these things are sort of useful in that way. And so here is an interesting problem. Talking about average value. So we're going to do a little exploration. You guys are going to have to do some calculations. And the question is, how long is the average chord of a circle? So here's what we got. We got a circle of radius r, and that is a chord of the circle. I don't know if you guys maybe haven't seen the word chord before, or you might have in geometry. Sort of depends on how far you got in your geometry class and who taught you. Don't think we got there. But a chord of a circle is just a line that runs from one point on the edge of the circle to another point on the edge of the circle. So it's a line segment that cuts through a circle. So we got the x-axis, we got the y-axis. And the first thing we need to do is come up with a formula for the length of that chord. Any thoughts on how we might do that? Any information that we know that you think might be helpful? Okay. Hint time. Right triangles. Right triangles are always wonderful. You ever wonder why we spent so much time on right triangles in geometry? Because they're wonderful. You see a right triangle? Where, Teresa? So that's not a triangle because it's a curve.
Oh, the other way, sorry. Because if you cut from like the 0, 0 point,
The 0, 0 point. Well, what's that called? The origin, excellent, thank you. From the origin to where? How long is that line right there? What?
Radius.
Radius. That's r. How long is this line right here? And now we don't know because that's going to change. But do we know anything about that little thing, that point right there? Isn't that x for our problem? That distance is x, agree? Yeah. How far is it from here to here? Keeping in mind what we're trying to find, which is the length of the chord, right? How long is that distance? Half the length of the chord. So I'm going to call that L over 2. And we'll define length of chord as L. And now we can relate those three values. L over 2 squared plus x squared equals r squared. Which means that the length of a chord of a circle is twice the square root of the difference between the square of the radius and the square of where the chord is. Does that seem reasonable? So I'm basically done, aren't I? I want to know the average length of that chord. Well, how do I find the average of any function? I just do this. So the average length of this chord is 1 over, well, b minus a, r minus negative r, because I'm going to do it from here to there. So I want the whole circle, times the integral from negative r to r of 2 square root r squared minus x squared dx. Next question. What does that thing there represent?
Area
Of what?
of the circle.
There it is. If I add up all the infinite numbers of lengths of chords, aren't I just adding up an infinite number of really skinny rectangles from one side of the circle all the way to the other side of the circle? Which means that's just the area of the circle. So the average length of the, average length of the chord is 1 over twice the radius times the area of the circle. And a little simplification says that that's pi r over 2. And wow, I didn't even need a calculator. And I didn't even need any actual numbers. As soon as we remembered, nicely done, Ethan, that integral is the area. And so that integral had to be the area of the circle. So, given any circle, the average length of the chord will just be pi over 2 times the radius of the circle. Where will it be located? Well, I want that to be this, and I want to know where it's located. So I got to solve for x, for that average chord, agreed? So the location of the average chord, well, L over 2, that's pi r over 4 squared plus x squared equals r squared, agreed? That means that x is equal to the square root of r squared minus, let me simplify that a little bit, pi squared over 16 r squared. Agreed? Stop me if I get it wrong. Guys, comfortable with factoring out an r squared? You want me to do two steps? Here, let's do 2 steps. Do we agree that this is r squared times 1 minus pi squared over 16? Which means that I can put the r outside of the square root. We good with that? Okay. I'm going to make this 16 over 16 because I can, because I want to. And so this becomes r over 4 times the square root of 16 minus pi squared. You okay with that? All I'm trying to do is I'm trying to make it easier by simplifying this. This is fairly complicated, and I'm just sort of doing some simplification to see if I can, again, being able to look at something and say, hey, I know roughly what that is without pulling out my calculator. Pi squared, approximately.
6. That's not sure.
Thank you for taking it back before I said anything. Pi squared, approximately. What's it got to be bigger than? Got to be bigger than 9, so I'm going to say 10. Square root of 16 minus 10, square root of 6, approximately. Got to be bigger than 2, but less than, closer to 2 or closer to 3, square root of 6. Closer to 2. So this is approximately half the radius. Approximately. Pretty decent approximation. But what that tells me is that the average chord will be found about halfway. Now, we could grab our calculators and figure out square root of 1 minus pi squared over 16 and see how close we are. Go. People with calculators. Square root of, just do the square root of this thing here. Let's see how close we are to, let's see how close this is to half. We don't have to do any of the simplification. See how close that is to half. How close were we? Nobody wants to say. Do we agree with 0.61? Teresa? Okay. You were just staring at it, but not nodding. And I was like, wait.
I was looking at that because I was confused for a second because I actually put the squared on the wrong side because I didn't put parentheses around the pi.
Oh, gotcha.
So
Gotcha.
like, what?
Yeah. So probably what we're looking at is we're looking at the fact that pi squared is actually probably a little less than 10. And then we're looking at the square root of something a little bit more than 6, which means it's higher than the 2 that we had ballparked. But ballpark is useful. You see, if it doesn't matter, if you don't need an exact value, I mean, clearly this has got to be somewhere near a half, 16 minus about 10, something about 2, sure. 2 divided by 4 is a half. We know it's not going to be, more than R, because our ballpark says, yeah, that's less than 4. So the mean value theorem of definite integrals applies here. We've just shown another example where it applies, and what we now know is that if you have a circle, the average chord length will be at about 60% of the radius of the circle, being a little more accurate than about a half. The average chord length will be walk 60% of the way out, and there's your average length. And we've shown that the mean value theorem applies for this problem. All right. Questions? Yeah. My house was hot when I got up this morning, which is annoying. It's an old house, 2 stories. I open all the upstairs windows and I get that flow, but I looked up, it was only 58 degrees, but that's still like 15 degrees more than it was in the morning 2 weeks ago. But it was 87% humidity in Blaine. So that didn't help. I was walking around the house going, oh my gosh, I'm already dying. Here's what I'm thinking. I've got one little section left that I want to talk to you guys about, and then I think we're going to call it good for calculus. I don't know what that means for next week. I got you guys Monday, Tuesday, and I'm assuming there's nothing going on. You've already taken your day off, seniors. Yeah. But there may be more.
One more thing.
What's the one more thing? Or you're not allowed to tell. I won't tell.
It doesn't involve this class. Yeah.
Okay. Because I won't tell.
We're good.
I don't remember how many years. Okay, anyway, let me know. Okay, before I get off track. I think we won't dive into 6.4. I think we're going to stop with 6.3. I've got one more little thing I want to talk to you about, which is the relationship between derivatives and integrals. We've got these integrals, which is area. We've already talked about derivatives, which is slope. I want to introduce you to that relationship between the two, derivatives and integrals, because it's an interesting relationship, and it sort of ties the two halves of calculus together. But I think what I'm going to do is I think I'm just going to take a few minutes tomorrow, and I'll just do that tomorrow. So I'm going to let you guys have the rest of the day as a work period. If you're all, there will be a 6.2 quiz dropping after school today. I wrote it last night. I'll give you a little bit of heads up. They're really, really good questions, I think. You guys really going to need to think about what they're asking. Don't go surface level on these questions. It's one of the things I notice in calculus is it starts out pretty straightforward and, you know, calculate this or find that. We're starting to get into the point where a lot of the questions that I'm asking you, like the, is this always true? A lot of the questions that I'm starting to ask you really require that you think about the ideas. It's not just a straight up, oh, you know, plug this into the calculator and get that number. Even problems as you move forward in calculus from here, even problems that are just a straight up calculation are still going to really require you to think about the context of the problems. What are they asking here? You know, what does this mean? Because the whole point of calculus and the whole point of what we're doing is that we're finally to the point where a lot of the math that you're doing means something. You know, the distance traveled by the ship for the 2-hour period from 7 to 9. It's not just, you know, it's not just solve this quadratic and you solve the quadratic and you write down 2 numbers and you move on to the next problem. So as you're just, you know, warning, heads up, advance notice, as you're reading through the questions tomorrow or this weekend, whenever you end up doing there tonight, whenever you do this quiz, really think about what it's asking. Really give some deep thought to, okay, what does this mean? And how does it relate to what the question is? And then does that make sense? Okay. So yeah. So work period, we'll finish 6.3 tomorrow. I think we'll be done with calculus. Next week, I don't know what we're gonna do Monday, Tuesday. You know, I can answer questions. We can. Oh yeah, Monday. Yes, Monday waffles. Yes. In fact, I was lying in bed thinking about that last night, and I thought,
oh boy, I need to sort of some way figure out how to not forget because I need to bring all the ingredients for waffles and I'm going to probably need to do some shopping and then remember to pack up all the waffle irons and bring them. I got to decide how many waffle irons to bring. I got 1, 2, 3, 4, 5, 6, 7, 8 of you. What's that?
I was sort of joking, but this is great.
No. I'm totally excited about it. Like I say, I got to figure out how many waffle irons to bring, which is weird. I could bring all of them, but one of them doesn't work right now. So so my first waffle iron was my grandma's. Did I tell you that when my mom gave it to me? She also gave me the newspaper clipping when my grandparents announced their engagement. And the newspaper clipping was John Leonard and Avril Haines have announced their engagement. Blah, blah, blah. They're Cannonsburg, Pennsylvania. And the staff bought them a waffle iron as an engagement present. And that's the waffle iron. And it's just like, that's so cool. And that would have been, my mom was the youngest, so that would have been sometime in the 20s. I'm not 100% sure where I'm sure it says, but it would have been sometime in the 20s. I found a company online. It was called Toaster Central. And he restores old toasters and sells them online. Well, at the time, he had a partner that did waffle irons. $140, including shipping, to send the waffle iron back to New York and have it completely restored. He soaked all the grease off using various processes. He disassembled the whole thing. He rewired it with all new wiring, and it came with a brand new plug because the old plugs are cloth and it was really frayed. And then it came with a copy of a photocopied thing on how to season waffle irons, because you have to brush oil on to season it, and you throw away the first batch of waffles you make as it seasons so that they won't stick, and it was just so cool. So then after I'd had several more waffle irons, I got one that was in a bit crummy shape. It was my aunt's. And my aunt and uncle are older than my mom. And so they had this old waffle iron from whenever. And I was like, you know what? I'm going to restore this one. It doesn't have any particular meaning to me. She was just like, well, none of my kids want it. It's in a box in the garage. Do you want this waffle iron? Okay. And so I stripped it all down and I did the whole process myself. Well, the problem I have is that the wire that feeds the power goes through a little hole in the metal. And it had Formica insulators, which are where they're actually a rock, but they flake off in really thin sheets, and they used them as insulators back then. It had a whole stack of them on each side. Well, they all, of course, crumbled because they're all 80, 90 years old. So they all crumbled when I was taking it apart. And so I got new insulators, not Formica. I can't get that thing to center in the hole, because when you start to tighten down the nut, it wants to move it in the hole. And I was putting a meter on the outside case of the waffle iron. It actually has voltage when you plug it in. It's like, so that thing is touching. As soon as you start to crank it, it touches one side. There wasn't anything in there to keep it from touching. Somehow they managed to center it perfectly in the hole when they built it. And I can't for the life of me figure out how to get it to do that. And I haven't been able to find just the right insulating washer with a little collar that sticks out that would go right into the hole. And I haven't been able to find anything. So there it sits. But yeah, I rewired the whole thing and I polished it all up, and it's really cool, but it doesn't work. So yeah, so there's that. So anyway, yeah, I'll have 3 or 4 different waffle irons here. I got one that's got 2 little tiny waffle irons. They're like 2 6-inch irons mounted on a rectangular base. So it makes 2 little waffles at a time, which I think is pretty cool. The rest of them are all just normal round waffles. Square waffles are an abomination. Yes, a total abomination. Nobody should make square waffles. And Belgian waffles, worse than square waffles. They're not even real waffles, really. So. All right. So yeah. What's that?
Squares. No.
Well, they fit in toasters better.
No, I was just trying to think like, what, they probably taste the same.
Oh, yes, they taste exactly the
But
same.
One's just way easier to cut. And it's the square.
Define easier to cut.
Like, when you cut it into strips.
Why would you cut it into strips?
Well, how are you supposed to cut it?
Wait a minute.
Well, you don't cut
Bite-sized
all the-
pieces?
You take the whole strip.
No. But it's easier to cut along the straight lines than around the whole curve.
Yeah, no, I had one square waffle iron. It was actually the second waffle iron I got. I was at a flea market in Anacortes. I was on my Harley, and he had this table that said free. And there was this Sunbeam square waffle iron, it was about yay big. And it was just sitting, it was from the 50s. All mine are from the 20s and 30s, but I was like, I was looking at it, and the guy says, yeah, it works. I've had it for a while. Nobody seems to want it, so I'm just giving it away. I was like, okay. So I'm walking around and, all my motorcycle leathers with a waffle iron under my arm. And then I actually gave that one to my sister. I think my little sister, Elizabeth, has that one because I said, hey, do you want a waffle iron? I'm going to get rid of this one. She was all excited to have a waffle iron, so. Yeah, but no, I'm a big fan of round waffles. They just make sense to me. You make a square waffle and then the corners are by the edges of your plate. How are you supposed to get syrup on those corners? Because they're way over there. Can't do it properly.
Just take them off with the
Are we all okay with real maple syrup, or should I bring some kind of fruit syrup as well? Do you guys like maple syrup?
I love maple syrup.
Okay, do you like real maple syrup? Have you had it?
I don't know, I have Costco maple syrup.
So no.
Okay.
I mean, when you say the Costco stuff, you're talking the stuff that comes in a jug like this, or you're talking the tall plastic bottles? Well, so maybe you have had real maple syrup. Yeah. Okay.
That sounds legit.
Well, I might grab a thing of like boysenberry syrup or something and bring it in case somebody tastes the real maple syrup and decides it's not their thing. Because it does not taste like, Mrs. Butterworth's maple flavored real maple syrup. So when you first taste it, it's like not nearly as sweet. You're like, wow, this doesn't taste like maple syrup because you're used to, Mrs. Butterworth's. But then after a while, doing real maple syrup and you go back to the artificial stuff and it's like, oh my God, this stuff's disgusting. Ew. Yeah, you spoil yourself. And then, real maple syrup is a lot more expensive. So then it's like, crap. Well, that's the nice thing about Costco. You get the big jug for 15 or 16 bucks. So yeah, I'll bring some alternative. I won't bring any Mrs. Butterworth's because I don't have any, but I'll bring some boysenberry syrup or something like that, so that if you don't prefer the maple, you can throw on the fruit stuff. So, all right. So yeah, tomorrow we'll finish up. Monday we'll have waffles. Tuesday, and then your seniors will all be gone. And then we're is it just Jerisa and Curtis? Okay, yeah, we'll do chapter 7.
Have fun.
We'll bang out the whole chapter Wednesday, Thursday, Friday, Monday, Tuesday.
Sounds great.
All right, cool. So work time, you got till 9:15, do your thing. If you're caught up on all your math, you're more than welcome to do other stuff if you got other stuff to catch up on. If this is the only class you have here, isn't this the only class you have?
I have English also.
Oh, okay. For some reason, I thought that you had this and then you left.
Well, I do leave
When's your English?
6 period.
Oh, okay. All right, cool. And I'll be happy to answer math questions if you have them also.
So there's no 6.3 assignment?
No, it's by the.
Have I not put a 6.3? I was going to put a 6.3, but not give you a quiz.
We just don't do either one.
What's that?
We don't need that.
back first.
I want you to have the practice though.
How about you
Up.
don't put up assignment, but we'll do practice on it.
Wow.
No, I think I'll put in a 6.3 because then you can get 5 more points, and maybe that makes a difference in your grades.
It might. I'm really close.
But don't you make homework only like 10%?
Even less for you,
Even less? Okay.
just for you though.
Okay, great. I can't remember, it was like,
It's been more this year because I've added, well, maybe not. Usually I just do homework and tests, but this year I've added all the quizzes. I don't know what percent it is. It's not a huge percent now, but no, I think I'll stick in a 6.3 assignment. You guys can turn it in before Tuesday and I'll give you 5 points and there won't be a 6.3 quiz. No, except for Teresa and Curtis and
There we go.
Finley.
really?
Probably, yeah.
Okay.
Probably.
Well, I gotta fill like a whole week for you guys, and we can't just sit around doing nothing for a whole week. I feel guilty.
I believe you made waffles for a whole week.
Great, and then I'll be 245 pounds by the end of the week after working really hard to not be.
You can also just let Curtis go off and like
Just let Curtis talk.
Just let him talk
A
and
whole week.
I know.
Or the week's over.
All right. Cool. All right. I will answer your question. Going to end the